Every small optimization matters. And here's the thing that really mattered: the RMS normalization, root mean square normalization. Basically, in the previous videos, I will have explained what layered means, layer normalization, batch normalization are about. They do simple things like they take the mean of the thing, like the mean of the values we have, the feature matrix, whatever it is. They'll take the variance and they'll do the standard deviation for this, add some epsilon to avoid it being zero, and do the x minus mean stuff. And after that, we'll just use the gamma and beta. We'll multiply this result, let's call it x naught or something, and add beta. And this is the scale, and this is the shift. And for modern LLMs, we need to eliminate few things because they want the output to be quite faster. The training should be done at a good pace. And basically, I learned something new today. This is also bias, the shift. I've been banging my head what shift is. I should have given some wrong examples at a one point. Now LLMs, they used RMS, root mean squared. As the name suggests, we'll take the root and the square mean, and this will just do the scaling part for us. And we'll just need the scaling at this point. We can ignore the shift because the value we got from RMS is stable. We'll get at a certain range. We don't resort to the off button like hitting zero or something. And just using RMS eliminated few steps, and eliminating that is quite useful for an thing like LLM. It is used in modern CLNs all that too, and layered is being still used by like these things, but and RMS is adopted by Llama, Mistral, maybe GPT at one point, because I don't know. We'll explore. And RMS is this simple thing, and most likely we see RMS not in maths. It belongs to maths, but basically you see this thing in physics. It is used to calculate the voltage, all that. Now let's write some code, and as you can see, we have eliminated the shift, and we are using that because it will eliminate some bias, all that, from normalization. If you still don't understand what I said, you can revisit the code that is there for layer normalization. You can always find that in code. And I have few doubts. Something like, if I eliminate bias, what about the training? What we are doing is in the normalization layer, not in the training layer. So it doesn't really matter. Now, let me write some code. I'll keep the solution handy. I don't want to fumble like I did in the last video. Let's take the RMS np.sqrt square root np.mean, and we'll square each and every value so that the justification is right. And we'll take the value in the end, the result, and we divide it by RMS, and we'll just apply the scale in the end. That will be np.round, and scale is gamma. to the value we got x hat comma 4, and we have to convert this to list from an empty array. And let's run this. Hope this will works. This will work. And done. It's pretty much easy, and I also recommend people to at least read the summary that is there, the motivation. You can skip the paper. Nobody can read all the whole paper in a day, not in a video at least. And layer norm something that looks like this. There are also other stuff too. How the baseline and layer norm looks. This is RMS, pretty straightforward, pretty simple. If you want to dive in, please do your research. And this is a simple video. In the next videos, we are going to learn about how to do training, what dead ReLU detector is. I already explained dead ReLU in some videos, but that isn't really dedicated to that. This training loop pretty much can be covered in a single video, because I'm not planning to solve the problems in a single video for this training loop. I'll make a collab notebook just like I did for normalization, PyTorch basics. Training will be like pretty much standard, and after that we'll dive into other things that I have missed when I'm when I'm explaining about this. Not really teaching. I'm not a teacher. Anyway, thanks for watching. Please like, share, and subscribe as always. Bye.